Ladies and gentlemen, welcome back to Engineering Dynamics. In this video, we will be again talking about the eigenmodes, eigenfrequencies, and the frequency response function. In this video, we will not be doing any derivation. We will just use the formulas to get all the things we need for the frequency response function for a given system. Let's jump right in. So we have this system. We have mass 1 that is moving along a rod and is connected to the wall with a spring. And we have another mass 2, that is connected to mass 1 and is basically just a pendulum. And now we want to find the eigenmodes, eigenfrequencies, and the frequency response function of this system. To do that, there's a step-by-step recipe, so a step-by-step solution that we will follow. So the first thing that you always have to do is get the equations of motion. These can be achieved either with the principle of virtual work or with the Lagrange equations. The next thing to do is find an equilibrium position. So where do we want to look at which position we want to look at the system? So this is number 2, find the equilibrium position. After that, we have to linearize the system because we don't want to work with sines and cosines and so on. We just want linear equations that are much easier to work with. This is now step number 3. Then we need to find the eigenfrequencies, and with the eigenfrequencies, we can find the eigenmodes. With the eigenmodes, we will then find the modal mass and modal stiffness. Then with those modal masses and modal stiffnesses, we will find the normal equations, so the uncoupled equations of motion that we can solve. Then after we did that, we will find the solution in the modal coordinates, and we want to transform those modal coordinates in the physical coordinates, so this is step number 9. And after we've done all this, we can find or draw the frequency response function and see how will the system react if I excite only one degree of freedom and how the other's degree of freedom will react to that. So let's follow that recipe and solve get the frequency response function for this system. We will not be covering the first 3 steps because we are already given the linearized equations of motion. So we will continue with step number 4. If you're interested in how to get to these equations of motion or to the linearized system, feel free to watch the other videos I did on that topic. So step number 4 is first find the eigenfrequencies. We find the eigenfrequencies. Let me get rid of that first. Remove. So we find the eigenfrequencies with the K and M matrix. So the K is our stiffness matrix and M is our mass matrix. In this case, we have M matrix right here and the K matrix, the stiffness matrix, right there. And we want to have them linearly, these equations of this matrix or this matrix linearly dependent on itself. So some rows are a linear combination of other rows. And this is why the determinant is 0. So we want to find a frequency where that is the case. And we do that by the determinant. So we will have this system and we basically just subtract K minus omega there and get a frequency 1 squared, that is 1.7, and a frequency 2 squared, that is 5.7. So just by doing that, we already know a lot about the system. We have a fairly low frequency and a fairly high frequency. Then with the help of the eigenfrequencies, we will find the eigenmodes. And here we have to solve a linear system. So we have our matrix. In this case, we insert one of the eigenfrequencies and find the corresponding eigenmode. So here, if we insert eigenfrequency 1, in this equation, we will get this matrix. And because it's linearly dependent, we can't solve for all the elements in our eigenmode. So we set one element, sorry for that, we set one element to 1 and determine the last one. To do that, we just simply multiply this one with that one and this one with this one, get this equation, and know the second component of our eigenmode. We do that for the first and second eigenfrequency and get the first and second eigenmode. We also can draw them. So if we have the simple system in gray, the first eigenmode is we move mass 1 unit to the right, and we change the angle in a positive, the angle anti-clockwise, so positive, and the system will look like this. If we look at the second eigenmode, we again move mass 1 unit to the right, but then we move our angle in a negative direction, so it will look like this. So you can imagine this system like this mass is on top of the pen and mass 2 is on the bottom. If we have the first eigenmode, it will vibrate like this. So everything moves in the positive direction and negative direction at the same time. If we look at eigenmode 2, the system will move something like this, where these masses move opposite to each other. So after we know that, we can get the modal mass and stiffness. And that is very, very simple. We just have to pre-multiply our eigenmodes that we found here on either the mass matrix or the stiffness matrix. And then we get the modal mass right there, 1 and 2, and modal stiffness. So we have now modal masses that describe the mass of the system and the modal stiffnesses that describe the system of our stiffness and the stiffness of our system at that specific eigenfrequency. So we already see that in where we have a higher frequency, we also have a higher stiffness. Because if we look at the equation, so if we have a larger eigen stiffness, we also need a larger frequency for a given mass matrix. So you know that this eigenmode is more complex than the first one, because here we move in the opposite direction. On the first one, we move in the same direction. The next thing we have to do is find the normal equations. And we know the form of the normal equations. So we have the modal mass times eta double dot plus the modal stiffness times eta is equal to 0. So now we can just insert these numbers that we found, and we will get these two equations. Of course, we can normalize them for the modal mass. So the modal mass is 0. That will look something like this. So we can just ignore it, and we will get this set of equations. So here we have the eigenfrequencies. So after that, we can find the solution in the modal coordinates. So the solution of those equations have this form, because if we have a eta and we derive it twice, only this function will give us the right solution. So we want now to solve for, we want to solve now for the b's and the a's. Here we have again the eigenfrequencies, and the same for the eta dot. We have a's, and here we have the sine, here we have the b's, cosine with the eigenfrequencies. But to solve this system, we need initial conditions, because we have a derivative twice in time. So we need those eigenfrequencies to determine not the eigenfrequencies, the initial conditions, to then determine those constants. So we have the initial conditions for our generalized coordinates is 0.1 and 0.1, and for q dot we have 0, 0. But now we have to transform those eigenfrequencies, we have to transform the initial conditions into the modal space and then solve the modal equations. So to transform it, we pre-multiply m and x on our q0 divided by the modal mass and get eta at 0.0. So we do that for 1 and 2 and get eta 1 and 2. Now, if we look at those equations at time equals 0, the sine is gone. So we only are concerned about this part. And because we know that the cosine at time 0 is 1, this is just 1, we already solve for A1 and A2. If we do the same thing for eta dot, we pre-multiply m, pre-multiply x r, so either x1 or x2, and here we have q dot, so this is our 0, divided by the modal mass. We get eta dot is equal 0, eta 1 dot is equal to 0, and eta 2 dot is equal to 0. So we already know that b1 and b2 are equal to 0. So now we are left with these two equations, or these two expressions for eta 1 and eta 2. And now we use those to transform them into the physical coordinates, because we know that the physical solution Q is a sum of the etas and our eigenmodes. So we have eta 1 times x1 plus eta 2 times x2. And this is our solution for our system, where we just input all the numbers we had, and we know the solution in the physical space. So if we now have our initial conditions and this equation, the solution is this right here. So it's very, very easy to get to that solution. But we're not done yet, because we are interested in the frequency response function. And the frequency response function will help us to understand what happens to each degree of freedom if we excite 1 degree of freedom of that system. So for example, if I apply a periodic force on the first degree of freedom, how will the second degree of freedom react? And here we have a very, very simple structure. First, we have 1 minus omega, that is our excitation frequency, of our rigid body modes, divided by the modal mass, but we don't have them, so we just ignore them for now. We only have to look at this part, where if we are interested in the k component, so component number k of our coordinates, generalized coordinates, when we excite coordinate number k. So if we jiggle at the first component, how will the first component react when we do that? So we have to take the eigenmode s and look at the component number k and divide by the eigenfrequency minus the excitation frequency squared divided by the modal mass. So in our case, the solution will look like this. So we have here the eigenfrequency, the modal masses. Here we have our eigenfrequencies squared right there and there. And here we have the dependence of our excitation frequency. And to solve this system, we always get this diagram where we start at a certain position, and if we approach our first eigenfrequency, the amplitude will reach infinity. So that's why this is our amplitude. We go up. But of course, we already know that from the last videos where we derived the frequency response function, we always know that we have a positive gradient. So after we went to infinity, we start again from the bottom, again move up, 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 up until we reach the second eigenfrequency. Then we again fall back down basically and go to 0. So here we already see again the special point of the anti-resonance. So this is right there. And this point is very special because this frequency is equal to the eigenfrequency of the pendulum. So if we excite our system, sorry, I should have mentioned that. So we excite our degree of freedom 1 with cosine times t, cosine omega times t. So we have our system and we pull on the spring. So we have a periodic force, a harmonic force in this direction. And there is a special frequency where if we pull on this mass will actually not move even because we're pulling, even if we're pulling, because the restoring force is actually coming from the second mass. So this is exactly the point where if we pull on one mass, the other mass goes in the other direction and counteracts the force that we are pulling with. So this is the point of the anti-resonance. So if this would be the same if we fix degree of freedom 1 and only allow the second pendulum to swing and look at the system again, we will find exactly this eigenfrequency. I hope this video gave you a better understanding on how to get the frequency response function. I'll just summarize it real quick. So we had a recipe that we had to follow where we got the eigenfrequencies and eigenmodes. Then we found the modal masses and stiffnesses, got our normal uncoupled equations in the modal space. Then we used that to find the solution in the modal space with the help of the initial coordinates, the initial conditions, because we need them because we have a system where we have a derivative in time twice. Then we transformed them with help of this rule to the physical space, and then we just used our frequency response function to analyze the system, how it will behave if we excite 1 degree of freedom and also then look at this degree of freedom. And then we found out that there are 2 frequencies, so our eigenfrequencies, where the amplitude will go to infinity, but there is also one specific frequency of excitation, so capital omega is our excitation, where the position of mass 1 is actually not changing at all. So it will stay fixed because the force that is needed to counterbalance comes from the second mass. So you only see eigenfrequencies with systems that have more than 1 degree of freedom. I hope this video gave you a better understanding about how to work with eigenfrequencies and eigenmodes and what we can use the frequency response function for. If you have any questions, feel free to ask them in the comments down below. I will be very happy to help. Thank you very much for your attention and see you next time.